central limit theorem together. Now, in every lecture, there are a few people who are new to the group. For the benefit of such people, these lectures are supposed to be academic entertainment lectures. So we go slow, we do not leave any question unanswered as far as possible. And we also encourage a lot of interaction and questions, comments, etc. Should not be a monologue at all. We started this series of probability lectures since 2020 July or August, if I'm not mistaken. So this is the 27th lecture, and we may try to maintain the frequency of once in 2 weeks. Now, these lectures, recordings and slides are religiously maintained, but I don't know about the accessibility. We'll have to look into that. Now, central limit theorem and law of large numbers are the two absolutely fundamental laws and theorems of probability. And since artificial intelligence has to deal with uncertainty, new situations, noise all the time, probability is our bread and butter. So here I may remark that long time back when we were students and we were doing AI, the AI systems used to be rule-based and knowledge-based. So human beings have a deterministic view of the world. And so I mentioned that these lectures are academic entertainment. So many times we digress into philosophical, humanities and social sciences, cognitive science oriented discussions. So as I was saying, when we were doing AI, the rule-based systems used to be the main paradigm. Okay, so a human being would sit down and write rules for solving an AI problem. Now, this has given rise to what is seen today as the paradigm of deep learning, where a lot of data is used to solve AI problems. So as I was saying, when we used to do AI and we would create rules, now human beings have a deterministic view of life, you see. Otherwise, I don't think we can operate with a lot of energy in the world. So if we think that if I do A, then B will result, we have a trust of that kind, confidence of that kind, and this confidence gives us energy and gives us the strength to move forward. So we have a deterministic view of life, and as we become more and more experienced and as we gain expertise more and more, we begin to see that there are always gray areas in everything. Okay, gray area is actually the law of life rather than black and white. So this was felt in 1960s and 70s when, for example, a system called mycin got created, and mycin was supposed to be a doctor's assistant. So a large number of rules got created, which is of the form that, let's say, if the eye color is yellow and the urine color is also yellow, then the individual has jaundice. So now you immediately spot difficulties here. Eye color can be yellow and urine can be yellow for many reasons. Okay, urine color can be yellow because of lack of water in the body. So eye color being yellow and jaundice and urine being yellow is one of the signals for the person to possibly have jaundice. Possibly have jaundice. How to capture this phrase? How to arrange for this kind of possibility. So this we know now very well. We know very well that it is probability which comes to our help in modeling this kind of situation. And mycin actually introduced what is called certainty factor, and certainty factors were values between 0 and 1. So 0.89 will have high certainty. So if the urine color is yellow, eye color is yellow, then jaundice, give a certainty factor, maybe 0.23, because there are many other signals required for ascertaining the person has jaundice. So what I'm trying to tell you is that though rule-based systems got created with a lot of confidence in determinism, it was seen that there is always ambiguity. The same set of conditions point to a large number of actions, okay, mutually exclusive actions, and we have to choose amongst them. So those of you who are doing machine translation, you know the alignment problem. You have parallel corpus. Delhi is a big city. Delhi bada shahar hai. So here, alignment of words. Okay, Delhi maps to Delhi or city. Okay, so there are multiple possibilities, and you have to choose one amongst them. And that choosing of one amongst them is a ranking scoring problem, which probability uh, gives us means for handling. Okay, so this is how probability came to be the bread and butter of artificial intelligence, and therefore in 2020 I decided that our group would do well to be well versed in the tools and techniques and concepts and foundations of probability. And when we do probability, we have to take note of important milestones. So central limit theorem and law of large numbers are two such milestones which are important for us, not only conceptually, but from practical point of view also. They tell us that you try to acquire as much data as you can. Data is gold. Data is important for all of us. And without data, we can't make any claim. And the claims would become very subjective, subject to our whims and fancies. Probability makes it principled. And you always have the backup option of going back to data and saying that, see, tell me, see, the data is telling me so and so. Okay. And you have a method of making a convincing argument. So central limit theorem and law of large numbers, we have started discussing. So today we'll do some mathematical work also. I'll go slowly over those steps. Now, the intuition for central limit theorem and law of large numbers was given. The larger the number of observations, the more accurate the probability value. This is a law. Okay, so just like if I leave an object mid-air, instead of going left, right, up, it goes down. Okay, and that is what caused Newton and many others who came before Newton to wonder, why does the object fall below? Why doesn't it go left, right, or up? Okay, so this is a law. We are talking about a law now. The larger the number of observations, the more accurate the probability value. This is intuitive, but this is also a law. Okay, so appreciate the law part of this statement. The larger the number of observations, the more accurate is the probability value. So we gave the example of our familiar problem, which is part of speech tagging. Part of speech tagging is covered in detail in CS 626, the first NLP course. Those of you who are doing deep learning for NLP course before doing CS 626 would appreciate this problem if you do CS 626 later. Okay, so this is like putting the horse before the cart, but part of speech tagging through statistical machine learning means is a very, very critical concept which should be acquired by any NLP student. Now, when we do hidden Markov model-based part of speech tagging, we use transition probabilities. Now, transition probabilities are learned from data, which is annotated corpus. So we have sequence of words, and we have a level called part of speech tag on each of these words, noun, adjective, verb, and so on. And from the data, we find out the probability of noun preceded by adjective, which is 0.8. So this kind of probability value is my parameter, and the parameter is of great importance because that is what will enable me to run the decoding algorithm, the Viterbi algorithm, and obtain the best possible probability of the sequence. So now when we say probability of noun preceded by adjective is 0.8, so this I know by calculating the values from the data. So we see how many times noun and adjective occur together divided by the number of times adjective occurs, and we get this value. Now, can we trust this value? We cannot if the labeled corpus is small. If the label corpus is large, we can trust this value. So this is the is the ground for applying the law of large numbers. So the probability of noun following an adjective is 80%. This is a claim about the whole population. Okay, we would like to say that in English language, the probability of finding a noun after I have seen an adjective is 80%. So there's a claim about the population. And I'm saying this based on what? How did I get 0.8? I got 0.8 from the sample. In the sample, I found that noun appears after adjectives 80% of the times. And from this, I am taking a leap of generalization, going to the whole population and saying that, yes, in English language, this happens. So there is a very big leap of generalization, and I must have a supporting law, okay, to convince everybody and to convince myself. So that law is the law of large numbers, and central limit theorem is a friend of law of large numbers. These two together is something that data science is founded on. Okay, law of large numbers and central limit theorem. This is the foundation for any probability-based work. Now, the intriguing part of law of large numbers, we are coming to the statement very soon. The intuition is stated here. I do not, and most often will not know the population average. I do not know the average height of people of India. Okay. And if I invest a lot of time, energy, and money, I can come to know of it. But by the time I finish all my data gathering, maybe a few other children have been born and people's age have increased, their height has changed. It is impossible. Okay, it is impossible to know the population average of India and even for Bombay, maybe even for Bombay, Delhi. What is the average income of people of all over the world? Very, very difficult to know. And many times it is impossible to know the average. Okay, but the intriguing fact is that I can converge towards it. Okay, not equality, but I can converge towards it. So this convergence is guaranteed by the law of large numbers, which says that as the number of observations increases, the trust or confidence in the value goes on increasing. Okay, so I take the n values, divide it by n, and then I have the average value. So this average value I can trust more and more as I see more and more observations. Okay, so this is one thing I want to point to you very emphatically, and would request you to be intrigued by this. Okay, even if you are not intrigued by anything, be intrigued by this, that without knowing a quantity, I can build confidence towards the value of that quantity because of the law of large numbers, and because as I go on accumulating more and more observation, I converge towards that number, and I have increasing confidence. I grow in confidence towards that, towards the estimate of that value. So again, I do not know the number. I will never know the number, but I will converge towards it. Okay, this is the law of large numbers. So that is why the probability of noun following adjective being 0.8, okay, I'll be more and more confident about that claim as my pause tagged corpus goes on increasing. As it goes on increasing, my confidence in that value also will increase. And I can very confidently apply that parameter for my Viterbi decoding. Okay, so now this very emphatically points to collecting more data. Okay, spend time, energy, money in collecting data. So now we come to the statement of the law of large numbers. First the weak statement and then the strong statement. Weak law of large numbers. Let x1, x2, xn be a sequence of independent and identically distributed random variables. Okay, each having mean EXI equal to mu, and we remarked it many times before, including the last lecture, that expectation always refers to the population. Okay, and the expectation of a random variable, expectation of the value of a random variable, you know, is equal to the sum of the product of the value into probability of the value. Okay, so what is the expected value of expected value? What is the expected value of Sarup? I saw your question. We'll get to that. So, what is the expected value of the of the sorry? What is the expected value that I can get when I throw a dice? Okay, so now the random, what is the random variable here? The outcome from the dice. Okay, see how you need to be very precise on every building block. So first and foremost, ask what is the random variable here. The random variable is the outcome after I throw a dice. What would be the values of these random variables? 1, 2, 3, 4, 5, 6. Okay, and then what is the expected value? Probability of 1 into 1 plus probability of 2 into 2 plus probability of 3 into 3 up to probability of 6 into 6. Now, if it is a uniform dice, then probability of 1 is 1 by 6. Probability of 2 is 1 by 6. Probability of 3 is 1 by 6. So the expected value will be equal to 1 plus 2 plus 3 up to 6 divided by 6. Okay, so that is the expected value. Now, expectation is always with respect to the population. Now, one point that comes to our mind is that you are saying probability of noun following the adjective is 0.8. And the law of large numbers is in terms of average value. Okay, so where is average in probability of noun given adjective? Probability of noun given adjective is 0.8. Where is average coming into picture here? Okay, so that is an important question. Law of large numbers is stated in terms of average. The probability value of a parameter we are interested in, okay, is not in terms of average. So where is the reconciliation? Okay, we need to see that. And we remarked last time that the bridge is provided by what is called the indicator variable. Okay, indicator variable. Anyway, so the weak law of large number states that if x1, x2, xn be a sequence of independent and identically distributed random variables, each having mean mu, then for any epsilon greater than 0, probability of the difference between sample average and the population average being greater than epsilon, okay, tends to 0. So you can make the difference between sample mean and population mean as small as possible, epsilon, okay, as small as possible as n tends to infinity. So what does epsilon depend on? Epsilon depends on the value of n, okay, how many data points you can gather. So the difference between sample mean and the population mean becomes smaller and smaller as n tends to infinity. That is captured much more intuitively by the strong law of large numbers, the strong version of the statement. Let x1, x2, xn be a sequence of independent and identically distributed random variables, each having mean as mu. No. Then for any epsilon greater than 0, that is not, this is due to copy paste. So this is not correct. 1 minute. Yeah. This will not be there. Yeah. So this statement is probability of the difference between uh, sample average and population average tending to 0 is 1. Okay, this is the strong version of the law of large numbers. It says that with probability 1, I can say that the sample average, the difference between sample average and the population average will tend to 0 as n tends to infinity. Now, why was the weak law introduced? Okay, why there are two versions, weak law of large numbers and strong law of large numbers? These are very interesting probability questions and theoretical questions. You can give a proof of the weak law of large numbers, weak law of large numbers, but cannot give a proof of strong law of large numbers. Okay, so at some point of time we will get into that. But you look at all this from a data science perspective. Okay, as we increase the data, what benefits do we derive from this, and what is the underlying principles? Okay, so now the important implication is that we can reduce the difference of sample average and population average. In other words, the sample average tends to population average by taking more and more data, okay, which is a very important action statement actually. So if I want to estimate the population average with sample average, just the law tells me that don't do anything, just keep increasing the data. You see, this is again a subtle point. You are not being recommended any action other than increasing your data size. Okay, so now here we know in today's deep learning world that yeah, getting more and more data is useful, but data should be of high quality, should be in usable form. The other option I have is to inject knowledge. Okay, so I have part of speech tagged labeled corpus. In addition, I use knowledge. I use the properties of noun, properties of adjectives. I use the knowledge that adjective cannot stand on its own. Okay, it is not a free word in that sense. It has the demand for a noun. So those kind of constraints are called knowledge, and they are introduced into the data science system. Okay, so the law of large number tells me that you are not required to take any option and take any action other than increasing your data. But we also say that what about injecting more and more knowledge? So this is an interesting perspective which we need to explore in the context of law of large numbers. So let's proceed. Okay. So the fact that I have to increase the data is very reassuring, though I know that I have to spend a lot of energy and time in this. Now, important implication is that x1 to x1, x2 up to xn summation divided by n tends to population average as n tends to infinity. So this is because of the law of large numbers. I can take these as the population mean as n tends to infinity. And this is surely true about the language properties also. As I collect more and more linguistic data, I can make more confident statements about language. Okay, so now we'll do some mathematical work, and we would like to give a proof of the weak law of large numbers. So here we are becoming technical mathematical. You'll excuse me because we need rigor in all these statements. If x is a random variable with mean mu and variance sigma square, that is the standard deviation is sigma, then for any value k greater than 0, the Chebyshev inequality says that probability of x minus mu greater than or equal to k is less than or equal to sigma square by k square. Okay, so Chebyshev was a Russian mathematician. So what we're saying is that the random variable getting a value which is beyond a radius of k decreases inversely with k square. Okay, decreases inversely with k square. And of course, if the standard deviation is smaller, then that also reduces the probability. So standard deviation, we know, is a measurement of the scatter of the data. Okay, while the mean or average gives you the measure of central tendency, the standard deviation gives you the measure of dispersion tendency. Okay, the tendency of the data to drift apart or move away from the mean. So look at the inequality once again. This inequality also can be proved, which I'll show just now. It says that the random variable taking a value which is greater than uh, k distance from the mu, okay, that probability is less than sigma square, the variance, divided by k square. So that probability decreases inversely as k square. So many of you would be reminded of inverse square law. Okay, so for example, electric field, magnetic field, they follow the inverse square law. As the distance increases, the intensity decreases. Inversely with the distance, square of the distance. So another form of Chebyshev equality I will come to, but let's take another inequality called Markov inequality, which also can be proved quite easily. If x is a random variable that takes only non-negative values, okay, then for any a greater than 0, probability of x being greater than or equal to a is less than or equal to expectation of x divided by a. So this is quite intriguing actually. This is due to Markov, and that inequality is stated this way. Take any value, and of course this random variable takes only non-negative values, 0 or positive values. So then the probability of x being greater than or equal to a, that probability is less than or equal to expectation of x, okay, that the population mean of random variable x divided by a. Okay, so this probability decreases in proportion to a, right? So this is an intriguing inequality. You can stare at it for some time. Probability of x greater than or equal to a is less than or equal to expectation of x divided by a, right? So this is the Markov inequality, and this is used to prove the Chebyshev inequality. So we use Markov inequality on x minus mu square. Mu is the population mean, with a being equal to k square. So we're doing some mathematical work. So probability of x minus mu square being greater than k square by Markov inequality will be equal to expectation of x minus mu square. Okay, this is the random variable now, x minus mu square, divided by a, which is equal to k square. So now x minus mu square can be greater than k square if and only if the mod of x minus mu is greater than k. Okay, x minus mu square can be greater than or equal to k square only if x minus mu mod is greater than k. So then I do this substitution here, and I see that probability of x minus mu mod greater than or equal to k is expectation of x minus mu square by k square. Now expectation of x minus mu square is nothing but sigma square, the variance. Okay, so this establishes the Chebyshev inequality based on a more fundamental inequality, which is Markov inequality. Okay, so we're doing some mathematical work here to establish the weak law of large numbers. Okay, so just one more time, Markov inequality, probability of x greater than or equal to a is less than or equal to expectation of x divided by a. The probability decreases inversely with A. Now we apply this with the observation that now my x will become x minus mu square. That is also a random variable. And A is equal to k square, the k I am interested in. So that establishes the inequality, Chebyshev inequality. Okay. Now there is another very nice form of Chebyshev inequality, uh, which takes us towards hypothesis testing, area under the normal curve, and so on. If x is a random variable with mean mu and variance sigma square, then for any value k greater than 0, probability of x minus mu greater than or equal to k sigma is less than or equal to 1 by k square. So this is a more elegant form of Chebyshev inequality. It says that the probability a random variable differs from its mean by more than k standard deviations is bounded by 1 by k square. Okay. So this inequality tells us something interesting, that the value of the random variable is not allowed to diverge, to go too far away from the mean. Not allowed. Okay. So if you want the distance between the value of the random variable and the mean to be some some k times of the standard deviation, then the probability of that happening is less than or equal to 1 by k square. So this probability decreases inversely with the square of k. You choose your own k, and this is what will happen. Okay, so you can picturize this to yourself, that the random variable is not allowed to drift too far away from the mean. That probability will go on decreasing as we go further and further. And if you bring in standard deviation, then you have a measure for this also. This probability is less than or equal to 1 by k square. So we have done three mathematical things. Markov inequality. Applying Markov inequality, we have proved Chebyshev inequality. And we have taken two forms of Chebyshev inequality, all towards establishing the weak law of large numbers. Any questions so far on this mathematics? No. Okay. And all these discussions are from this beautiful book on probability by Sheldon. Okay. Probability for scientists and engineers. Now we would like to complete the proof of weak law of large numbers. Okay. So we have this observation that expectation of x1 plus x2 up to xn divided by n is equal to mu. Okay. And the variance is, expectation of x1, x2 up to xn divided by n is equal to mu. This is because of the linearity of expectation function. So this is 1 by n into expectation of x1 plus expectation of x2 plus expectation of xn. Each of these expectation is mu. So we have n into mu divided by n, which is equal to mu. And variance of x1 plus x2 up to xn divided by n will come out to be equal to sigma square by n. Okay, so this is also quite easily provable. Okay, you just have to remember the basic definitions of variance, expectation, and so on. And expectation as variance, as you know, is expectation of x minus mean square, mean whole square. If we apply the Chebyshev inequality now, then probability of x1 plus x2 up to xn divided by n minus mu being greater than epsilon will be less than or equal to epsilon sigma square by n by epsilon square. Okay, so sigma square by n is the variance, okay, this whole thing, divided by epsilon square. Epsilon is our k. Okay, so we are using this form of Chebyshev inequality. This form of Chebyshev inequality. Probability of x minus mu mod greater than or equal to k is less than or equal to variance by k square. Now make k equal to epsilon, and the weak law of large number is arrived at. So probability of the sample average minus population average being greater than epsilon is less than or equal to variance by n sigma square, n epsilon square. Now you can see that as n tends to infinity, this quantity on the right hand side becomes smaller and smaller. This tends to 0. Okay, so therefore we get the statement of the weak law of large numbers. Probability of sample average minus population average being greater than epsilon tends to 0 as n tends to 0. This is the statement of weak law of large numbers. Okay, and this is the proof also. So the proof makes use of, first of all, definition of expectation, linearity property of expectation, definition of variance, and application of Chebyshev inequality. Okay, so now we are on firm ground. We have proved the weak law of large numbers. Any question at this point? Okay, no. So now we would like to motivate central limit theorem, and we'll take up a practical problem called sand problem. So in 2020, we had introduced this problem and discussed it. Now it is about 2 years, so we can go back to it and use it to motivate central limit theorem. So here is the problem statement. We have to estimate the percentage of sand grains in a pile of sand resulting from the fragmentation of a mineral compound which fall in a particular range. Okay, so we have to estimate the percentage of sand grains which fall in a particular range. That is the main problem. And then we have elaboration of the problem in terms of this piece of text. In a pile of sand resulting from the fragmentation of a mineral compound. So when we do mining, these kind of mineral particles accumulate, and these mineral particles are useful. Okay, mineral sand is an essential component of consumer products such as paint, plastic, paper, etc. Okay, and almost all titanium minerals are used as feedstock to produce titanium dioxide pigment, which is used in products such as paints, paper, and plastic. So these mineral particles are useful for many practical need. And for the purpose of paints, for example, the sand particles should be in a range of sizes. So we have to manufacture paints, and paints need mineral sand particles. And those have to be in a range for the consistency of the paint. That is the big picture. So there is a similar problem. We want to estimate the percentage of people in Mumbai who are employable as construction labor. And this is the set of people with age range between 18 to 58. Okay, so so this kind of data are always required for decision making. Now we come back to the sand grain problem. A sample of 10 grains is taken from a large pile, and they have these respective sizes: 2.2, 3.4, 1.6, 0.8, 2.7, 3.3, 1.6, 2.8, 2.5, and 1.9. So looking at this sample, would you like to make a guess about the range distribution in this pile of sand particles? So estimate the percentage of sand grains in the entire pile whose size is between 2 and 3. Okay, so this is the sample in front of me, and I am controlled completely by the data in front of me. So if you look at these numbers, I think for this sample at least, you can see what proportion is in the range of 2 and 3, just by observation. So we'll come to all this. We first take a naive approach to solving the sand particle problem. So sample size for us is 10. This is the data. Sizes are this. So number of particles in the range 2 to 4 is 4. 2.2, 3.4 is in the range. 1.6 is not. 0.8 is not. 2.7 is in the range, and so on. So the percentage is 4 by 10. This is 40%. So you see, now I'm making a claim. I'm saying that 40% of the sand pile, in the sand pile, 40% of the particles here, okay, in this almost infinite number of sand particles, 40% is in the range 2 to 3. And how am I making this claim? Only from 10 samples. Only from 10 samples. Now you see, the law of large numbers gives me one confidence. It says that as I take more and more sand particles, I will have more and more confidence in this proportion. Right now it is 40, but with more sand particles, I will revise this. And as I take more and more sand particles, I'll give you better and better estimate of this range. Okay. But right now, with this 10 sample points, my claim is 40%. Am I correct? Okay. Am I correct? So may or may not be. If it is correct, then we get this correct value by chance, purely by chance. And there is no principle behind this. So if somebody challenges me, I have nothing to fall back on. So I have to be firmly grounded. I need some more instruments to say that, I am very confident. And the confidence is, of course, guided by the data size, quality. We are not saying anything. When will the conclusion hold for the whole population? Does 40% in the range 2 to 3 hold for the pile? Okay, so hypothesis testing and other things. Now it turns out that there is something very interesting in this whole problem. There is an interesting twist to the problem. Okay, so am I audible so far? Screen is visible. Can somebody verify?
Yes, sir.
Yes, sir.
So I have the naive way of estimating the proportion, but here is introduction of a more powerful piece of knowledge. More powerful piece of knowledge. So that is why I insist on getting a clear understanding of the task. We are strengthened by the knowledge of Kolmogorov's law of fragmentation. Kolmogorov also was a very well-known Russian mathematician. The size of particles resulting from the fragmentation of a mineral compound has log normal distribution. Log normal distribution. Okay. What it means is that a random variable x has a log normal distribution if log x has a normal distribution. Okay. Once again, a random variable x has a log normal distribution if log x has a normal distribution. So y is equal to log x, and f of y, which is the probability density function of y, is given in this form. It is fy is equal to 1 by root 2 pi into sigma. Sigma is the standard deviation of the population, into e to the power y minus mu. Mu is the population mean square, divided by 2 sigma square. Sigma is the standard deviation. So this is this formula is known to all of us. Okay, the form of the normal distribution. What is very interesting about this discussion is the contribution of science, and in particular mineral science and material science, okay, material properties and so on. Somehow we know that the size of particles resulting from the fragmentation of a mineral compound has log normal distribution. Very interesting. And the light of science is now shining on our discussion. the light of science is shining. Okay, I have additional knowledge which I can inject into the system now. The additional knowledge is that the size of particles resulting from fragmentation of a mineral compound is log normally distributed. This is an additional information, and in the naive estimate of proportion, I have not used that knowledge. I am throwing away that knowledge, which is naive on my part. I should not waste knowledge. Okay, so this way of calculating the average is discarding quite criminally, I would say, an important knowledge, which is the fact that these particles are log normally distributed. I am committing little more sin. This way of calculating proportion is making a hidden assumption that I am making use of some form of multinomial distribution. And I am wide of the mark. The distribution is not multinomial. The distribution is log normal. Okay, that is the reality. That is the underlying reality. How can you use a distribution which is not the actuality? How can you make use of knowledge, quote unquote knowledge, which is false? Okay, then your calculations and deductions and inferences will be all wrong. So let us see that in light of this revised knowledge, what can we do? So we have to make use of this knowledge, and there is a way. The percentage of sand particles in the range 2 to 3, this percentage actually translates to probability. Okay. How does percentage translate to probability? What is the relation between ratio of counts becoming probability? Where does it come from? Okay, this is the frequentist view of probability and should be contrasted with Bayesian view of probability. But it is very difficult to get away from frequentist view because Bayesian probability actually makes use of prior probability. Posterior probability is a function of prior probability. And for prior probability, if you apply again Bayesian probability, then you will have to make use of another prior probability somewhere and add infinitum. Every prior probability, if I want to get that value by Bayesian theorem, I'll have to make use of another prior probability. So at some point of time, we'll hit a wall and we'll have to make use of frequentist view of probability, which is ratio of counts. Ratio of counts is percentage and can be equated with probability because of what? Because of, again, law of large numbers, hypothesis testing, central limit theorem, and so on. Okay, so these subtle and intricate connections is what we want to look at in these discussions on probability, the probability and AI connection. So our goal is to find the probability of the sand particle size falling in the range 2 to 3. Okay, and here we are helped. We know that the sand particles follow log normal distribution. That means if you take the value of the size and you take the logarithm of that, then those log values will fall in a normal distribution. So we want to get this log x value within the range log 2 and log 3, and we want to get the probability of that. So this is possible by means of what is called the Z score and normal distribution. Okay, we have to make use of the standard normal distribution whose mean is 0 and standard deviation is 1. So last year we saw many examples of how to make use of the Z score and the Z score table, and the Z score table will give me the probability of this range being 32.32. So not 40%. The use of the knowledge of log normal distribution says the proportion of sand particles falling in the range 2 to 3 is 32, not 40. Okay, and that's a more correct and more principled statement. And in reality also this will hold out. If you go on increasing the amount of sand particles and observing their size, the measurement tending to 32% and not 40%. The reason for 40% was wrong assumption about underlying probability distribution. Now we still have to connect a few dots. We are getting the probability to be 32% from probability. We are getting the probability of the sand particle falling in the range 2 to 3 is the 0.32. And from there, we are saying that the proportion of sand particles in the range 2 to 3 is 32%. Probability 0.32 from that 32% is a big leap. This is again a gap which needs to be closed. And I insist that you do this kind of intricate theoretical thinking. How from probability you are able to make statement about percentage? Are you not implicitly making use of the frequentist definition of probability? You are actually. So 32% and probability of 0.32, they are being linked by frequentist view of probability. Will I get a different answer if I had taken Bayesian framework? An interesting question. Okay, so I've stopped now because we have just about 3 minutes left. I believe there was a question from Swaroop. Swaroop, what was the question? You put it on
How
the
does
chat.
regularization relate? Yeah. So how does regularization relate with the law of large numbers? Because we are often advised to use regularization in presence of low amount of data.
Low amount of data. Achha. So no. So you say regularization comes in when it comes in to prevent overfitting. No? So yeah, right. You're right. That there is disproportionate number of parameters, large number of parameters, and disproportionately small amount of data. That is the situation, right? Swaroop?
Yes, sir.
Yeah. So the number of parameters are huge, the amount of data is small. So very conveniently, the machine learning model, what it does is that it asks every parameter to take charge of one instance of the data, and thereby at least satisfy the training requirement. So the parameters are very large, and a small set of parameters take charge of one instance of data, and there is no generalization happening. No generalization happening means what? You do not find a surface, a learning surface, which passes through the data such that it represents the whole data. Instead, you have a surface which goes through each and every element of data, okay, sitting on each of them, and not really generalizing to an intervening surface. So this is overfitting, and regularization is recommended to solve this problem. So what regularization does is that it forces the learning surface to be independent of the training data. It captures the essence of the training data, but does not sit on each and every data. Okay, so if I'm doing face recognition, so if I'm doing, let's say, cat versus dog recognition, then instead of observing each and every cat in the model, I capture the essence of catness, essence of dogness. Essence of catness is round face, and essence of dogness is a conical face. Okay, that is a discriminating feature by which I can do this decision making. Now this essence is not same as the instance. Essence is not same as the instance. Essence is a part of the instance, a property of the instance, but it's not same as the instance. So the learning surface doesn't go over each instance, but it goes over the essence. That is what achieves learning and generalization. Okay, and regularization prevents that. Now let us come to your question. The question was, how does law of large number relate to regularization? Is that the question?
Yes, sir.
How does it relate to? Is it relate to? Can you explicate relate to? What does relate to mean?
So, sir, law of large number states that we need to have a large amount of data in order to have a good estimate of the surface.
Yeah.
And regularization says that use me in order to prevent like overfitting to small amount of data.
Yes, yes, yes. So regularization is a knowledge injection, a form of knowledge injection. Okay. So in the support vector machine, when you take that square term, for example, you are making use of a constraint which is not really the property of the exact problem. So the support vector machine for distinguishing cat from dog. Okay. So there you introduce a quadratic term for regularization, thereby saying something about the property of the data, which is independent of cat versus dog or table versus chair, any kind of binary classification. So regularization actually is reducing the data requirement by injecting knowledge. That is some problem constraint which is independent of the problem itself.
Okay. Okay.
Yeah. So that's a good point. So can we sort of evade the law of large numbers? Can we sort of not evade? Can we uh, uplift ourselves out of the constraints of law of large numbers? Because law of large numbers says that you have no option. Do not do anything other than just increasing the data to have more and more confidence in the machine learning models and the learning models performance. Just increase the data. Okay, go on. Very good advice. We'll do that. And we have seen historically also the impact of this law of large numbers. Machine translation used to be statistical. Okay. When the data became humongously large, then we threw away statistical machine translation. We brought in NMT, neural machine translation. Okay, and then when a lot of data became available, rule-based and machine learning-based systems for ImageNet data were sacrificed. Neural methods came in. ASR challenge on switchboard data, again deep learning asserted itself because the data became large. And law of large numbers is again playing its role, saying that, see, if you increase the data size, your paradigm also changes. Okay, you will surely pick on me saying that, sir, you're making lots of claims. You are not using the word average at all. Are you not sort of fantasizing? Are you not fantasizing? Because law of large numbers is based on average. How are you allowed to say all these statements? Okay, I can, because you see there are bridges between average and each of these problem settings. There are bridges. Okay, indicator variable is one bridge. We would like to see that. We'll take many NLP problems and see how to convert and get out of this constraint of averages. So, historically, practically also, we have seen paradigm shift because the data became more and more in size. Okay, advent of data is paradigm shifting. It strikes a blow at the established knowledge. This happened before also, when black body radiation started questioning the foundations of physics. When speeds, very high speeds, started to question the foundations of mechanics, Newton's laws of motion. Okay, so all this happened and everything is caused by data. All right, so I think we'll stop today and finish the session. Okay, thank you.